What If? Serious Scientific Answers to Absurd Hypothetical Questions, by Randall Munroe. Introduction. What would happen if you tried to hit a baseball pitched at 90% of the speed of light? It's a question that sounds like it belongs in a comic book, not a physics textbook. And yet, the answer involves nuclear fusion, a bubble of expanding plasma, and a mushroom cloud that would wipe a city off the map. It ends not with a home run, but with a crater. This is the strange, wonderful, and utterly brilliant world of What If? A book that takes the most absurd hypothetical questions you can imagine and answers them with rigorous, scientific seriousness. It's a place where curiosity is not just welcome, it's the only rule of the game. The mind behind this delightful madness is Randall Munroe. Now, this isn't just some clever writer. Before he became famous for his stick figure webcomic, XKCD, Munroe was a roboticist at NASA. He's a man who has worked on the very edge of what's possible, building machines to explore other worlds. And it's that unique background, that blend of playful imagination and hard-nosed scientific reality, that makes this book so special. He left NASA to draw comics, but he never lost his love for science and math. Instead, he found a new outlet, answering the internet's weirdest and sometimes most worrying questions. What If? Became a cultural phenomenon, selling millions of copies and showing an entire generation that science isn't just about memorizing formulas in a stuffy classroom. It's a tool for exploring the universe, a key that can unlock the answers to our wildest wonders. It reminds us of that childlike joy of asking why, and what if, questions we too often forget as we grow up. Today, we're going to step into that world. We're going to explore what happens when you push the laws of physics to their absolute limits. And I promise you, by the end of our journey, you will not only have the answers to questions you never thought to ask, but you will also rediscover the profound, exhilarating fun of looking at the world and simply wondering, what if? Book summary. Let's begin our journey with a question that feels both simple and world-ending. It was asked by a reader named Andrew Brown, and it goes like this: what would happen if the Earth and all terrestrial objects suddenly stopped spinning, but the atmosphere retained its velocity? The answer, in a word, is chaos. But the details are where things get truly interesting. At the equator, the surface of our planet is moving at over 1,000 miles per hour, about 470 meters per second, as it spins on its axis. If the Earth suddenly stopped and the air didn't, the result would be an instant, global wind of unimaginable force. For the vast majority of the world's population, about 85% of us who live between 42 degrees north and south, this wind would be supersonic. Imagine a wind so powerful it moves faster than the speed of sound. For a few brief minutes, this torrent of air would scour the surface of the planet. Friction with the ground would eventually slow it down, but not before it had reduced virtually every human structure to rubble. Skyscrapers, houses, bridges, all would be torn from their foundations and sent tumbling across the landscape like dust. Even in cities far from the equator, like Helsinki, Finland, the winds would be stronger than the most powerful tornadoes ever recorded. No building would be safe. And it's not just the wind itself you'd have to worry about, it's what the wind is blowing. Even if you were in a nuclear-hardened bunker, your neighbor's less sturdy house would become a 1,000-mile-per-hour projectile aimed directly at you. Survival would be a matter of pure luck. Anyone on the surface would be pulverized by flying debris. The only survivors would be those who happen to be deep underground, in a subway tunnel or a deep basement, perhaps. And, of course, the scientists at the Amundsen Scott Research Station at the South Pole. For them, the first sign of trouble would be an eerie, profound silence, as the entire world of communication suddenly went dead. And then, someone would notice something even stranger: the sun wasn't moving. As the surface winds died down, the world would get even weirder. The immense kinetic energy of the wind would be transformed into heat, scorching the land and triggering global thunderstorms where the air was moist. The wind sweeping over the oceans would churn the surface into a chaotic mix of spray and sea, making it impossible to tell where the water ended and the air began. This tempest would dredge up cold water from the ocean depths, creating a bizarre new kind of weather, a swirling, roiling blend of wind, fog, and violent temperature swings. A colossal storm surge, the largest in world history, would sweep around the globe, with a wall of water advancing like a tsunami for miles inland. And with the Earth no longer spinning, the cycle of day and night would end. Day and night would each last 6 months. The side of the Earth facing the sun would bake under constant light, while the night side would plummet into a deep freeze. It seems like the end of everything. But in this catastrophic scenario, we would have one silent, steady friend: the moon. You see, right now, the Earth spins faster than the moon orbits it, and the tides created by the moon are actually slowing our planet's rotation down, ever so slightly, while pushing the moon farther away. But if we stopped spinning, the reverse would happen. The moon's gravity would gently, relentlessly tug on our silent planet. Instead of slowing us down, its tides would begin to accelerate our spin. Slowly, over an immense timescale, the moon would work to undo the damage, and the Earth would start turning once again. It's a terrifying thought, imagining our entire planet being subjected to such a cataclysm. But what happens when you take that level of cosmic energy and focus it on something much, much smaller? What happens when the disaster isn't planetary, but is instead confined to a single baseball diamond? This brings us to one of the most famous questions Randall Munroe ever answered. What would happen if you tried to hit a baseball pitched at 90% the speed of light? Let's imagine it. A normal game, a normal pitch. But in the instant the pitcher releases the ball, it magically accelerates to 0.9 c, that's over 600 million miles per hour. From that point on, everything happens according to the normal laws of physics. The ball is moving so fast that everything else in the world, including the air molecules in front of it, is practically standing still. Aerodynamics don't apply here. The air doesn't have time to flow around the ball. Instead, the ball smacks into the air molecules so hard that the atoms in the air literally fuse with the atoms on the ball's surface. Each of these microscopic collisions releases a burst of gamma rays and scattered particles. These expand outward from the pitcher's mound in a bubble, ripping electrons from their nuclei and turning the air in the stadium into an expanding sphere of incandescent plasma. This wall of energy and radiation would approach the batter at nearly the speed of light, arriving only fractions of a second before the ball itself. The constant fusion at the front of the ball acts like a rocket engine, pushing back on it and slowing it down. But the ball is moving so incredibly fast that even this ongoing thermonuclear explosion barely makes a difference. It does, however, start to eat away at the ball's surface, blasting off tiny fragments. These fragments, also moving near the speed of light, trigger their own fusion reactions when they hit other air molecules. After about 70 nanoseconds, what's left of the ball reaches home plate. The batter wouldn't even have seen the pitcher release it, since the light carrying that image would arrive at about the same time. The ball itself is no longer a ball. It's a bullet-shaped cloud of expanding plasma, mostly carbon, oxygen, and hydrogen, still triggering fusion as it travels. The shell of X-rays hits the batter first. A few nanoseconds later, the plasma cloud arrives. It would hit the bat, the batter, the catcher, and home plate, scooping them all up and carrying them backward through the backstop as they completely disintegrated. In the first microsecond, the bubble of superheated plasma would swallow the backstop, both teams, the stands, and the entire surrounding neighborhood. If you were watching from a safe distance, on a hilltop outside the city, the first thing you would see is a silent, blinding flash of light, far brighter than the sun. This would fade over a few seconds, replaced by a growing fireball that rises into a mushroom cloud. Then, with a deafening roar, the blast wave would arrive, tearing up trees and shredding houses. Everything within a mile of the park would be leveled. The baseball diamond would be gone, replaced by a sizable crater. And the batter? Well, according to Major League Baseball Rule 6.08b, the batter would be considered hit by pitch, and would be eligible to advance to first base. It seems that whether the force is planetary or microscopic, unleashing that much energy rarely ends well. But not all extreme scenarios are about destruction. Some are just strange. Consider, for instance, a question from a reader named Sean Rice. What would happen if you were to gather a mole unit of measurement of moles, the small furry critter, in one place? First, we need to understand what a mole, the unit, really is. It's not like a pound or a meter, it's just a number, like a dozen or a billion. It's a very, very big number, 602 sextillion 214 quintillion 129 quadrillion. It's a number so large we use it to count things like atoms and molecules. So, what would a mole of actual moles, the burrowing mammals, look like? Let's do some quick, rough math. A mole is an animal small enough to hold, so let's say it weighs about 75 grams. If you multiply that by the number of moles in a mole, you get a total mass of about $4.52 times 10 to the power of 22 kilograms. That might not mean much to you, but it's a little over half the mass of our own moon. We're talking about a planet-sized mass of moles. If you were to gather them all in space, their own gravity would pull them together into a sphere. You would have a new planet in our solar system, a planet made of meat. It would be slightly larger than the Moon, with a surface gravity about 1/16 of Earth's. And this is where things get gruesome. The immense pressure in the planet's core, over 100 megapascals, would be high enough to instantly kill any bacteria, sterilizing the mole remains. This means most of the planet wouldn't decompose in the normal way. Near the surface, however, where the pressure is lower, anaerobic bacteria, those that don't require oxygen, would begin to break down the mole tissue, releasing a tremendous amount of heat. This process would heat the planet, but it would be self-limiting. As the temperature rose, the bacteria would die off. The outer surface would radiate heat into space and freeze, forming a literal fur coat that would insulate the planet's liquid interior. Plumes of hot meat and trapped gases like methane would periodically erupt through the crust in what could only be described as geysers of death, blasting mole bodies out into space. Eventually, after millennia, the planet would cool and freeze solid. The water within the mole bodies would crystallize under the immense pressure into exotic forms of ice, like Ice V and Ice 9. It's a bleak and bizarre picture. But as Munroe points out, there's a better way to think about this. There might be 1 billion habitable planets in our galaxy. If we colonized even a fraction of them, and brought small mammals with us, then over a few million years, the total number of moles that will have ever lived would easily surpass Avogadro's number. So if you really want a mole of moles, you don't need a magical portal. You just need to build a spaceship. From the cosmic to the biological, the questions in this book span every imaginable scale. But some of the most fascinating questions are those that deal with us, with humanity, our society, and our own limitations. What happens when you gather not a mole of moles, but all of humanity in one place? A reader named Thomas Bennett, along with many others, asked, what would happen if everyone on Earth stood as close to each other as they could and jumped, everyone landing on the ground at the same instant? First, the jump itself. The entire population of Earth, crowded together, would take up an area roughly the size of Rhode Island. At the stroke of noon, everyone jumps. Does it affect the planet? Not really. The Earth outweighs us by a factor of over 10 trillion. The push from our jump would move the planet by less than the width of a single atom. So, the jump is a bust. Everyone lands. The sound of billions of feet hitting the ground would create a loud, drawn-out roar, but that's about it. The real story begins after the silence returns. Everyone is in Rhode Island. All 7 billion of us. And no one knows how to get home. The first thing that happens is that every cell phone network on the planet collapses. Billions of phones, all in one place, all searching for a signal. The system would be overwhelmed in an instant. Outside of Rhode Island, the world, now empty of people, would grind to a halt. Power plants would fail, machinery would stop, and an eerie silence would descend upon our abandoned cities. Back in Rhode Island, chaos ensues. The airports, even running at maximum capacity, couldn't make a dent in the crowd for years. The highways, I-95, I-195, I-295 would become the sites of the largest traffic jam in human history as people commandeered cars, only to run out of fuel a few miles later. The crowd would begin to spread outward, into southern Massachusetts and Connecticut. But there's a problem. Almost no one speaks the same language, and almost no one knows the area. Society would break down. Violence would be common. Everyone would be hungry and thirsty as grocery stores were emptied in hours. Fresh water would become the most precious resource, but with no system to distribute it, it would be almost impossible to find. Within weeks, Rhode Island would become a graveyard of billions. The few survivors would spread out across the empty continents, struggling to build a new civilization from the pristine ruins of the old one. Our species would survive, but it would be a shadow of its former self. The Earth's orbit, of course, would be completely unaffected. It would spin on, just as it always had. But at least we'd finally have the answer to what would happen if everybody jumped. From the fate of humanity to the fate of a relationship. What if the connections we feel weren't just a matter of choice and chemistry, but were pre-written in the stars? A reader named Benjamin Stafford asked, what if everyone actually had only one soulmate, a random person somewhere in the world? What a nightmare that would be. First, let's establish the rules. Your soulmate is a real person, chosen at random. You don't know who they are, but you'll recognize them the instant your eyes meet. The first problem is a grim one. 100 billion humans have ever lived, but only about 7 billion are alive today. If your soulmate was chosen from everyone who has ever existed, there's a 90% chance they're already dead. And because of how time works, we'd also have to include people from the future, meaning your soulmate could be someone who won't be born for another 1,000 years. So, let's make it a little easier. Let's say your soulmate is alive at the same time as you, and is close to your own age. This gives you a pool of about 500 million potential matches. The odds are still staggeringly against you. Think about how many new people you make eye contact with each day. Maybe a few dozen, if you're outgoing. Over a lifetime, that might add up to 50,000 people. Given a pool of 500 million potential soulmates, this means you would find your true love in only one lifetime out of 10,000. The vast majority of us would live and die alone. In such a world, society would completely restructure itself to maximize eye contact. We might build massive conveyor belts to move lines of people past each other. Or, more realistically, we'd use technology. Imagine a global version of chat roulette, where people spend hours a day, 7 days a week, staring into the eyes of strangers, hoping for that one spark of recognition. But even then, it would take decades to match everyone up, and few people could afford to devote their lives to such a search. Jobs like cashier or police officer in Times Square would become high-status careers, prized for their eye contact potential. People would flock to cities, just as they do now, but with a desperate, frantic energy. And in a world with so much pressure to find the one, many people would simply fake it. They would find another lonely person, stage a public soulmate encounter, and live out their lives pretending to be happy, hiding their deep, unshakable loneliness from their friends and family. A world of random soulmates wouldn't be a romance. It would be a tragedy. It would be one of the loneliest worlds imaginable. Let's hope that's not the one we live in. The questions we've explored so far have been about physics, biology, and society. But Randall Munroe's background at NASA often leads him to questions about the final frontier, space. And his answers reveal just how counterintuitive the physics of space travel truly are. Several readers ask questions that all touch on a common misunderstanding about getting into orbit. They ask things like, couldn't a spacecraft slow down to a few miles per hour on re-entry to avoid needing a heat shield? Or couldn't a rocket just be lifted high into the atmosphere to make it easier to get to escape velocity? The answer to all of these questions hinges on one profound, fundamental idea. The reason it's hard to get to orbit isn't that space is high up. It's hard to get to orbit because you have to go so fast. Space is only about 100 kilometers away. That's not as far as it sounds. For many people on Earth, space is closer than the nearest ocean. Getting to space is relatively easy. You could launch a person there with a rocket the size of a telephone pole. The challenge isn't getting there, it's staying there. When you're in low Earth orbit, like the astronauts on the International Space Station, you are still very much in the grip of Earth's gravity. In fact, the pull of gravity is about 90% as strong as it is on the surface. The reason astronauts float is not because there's no gravity, it's because they are in a constant state of free fall. They are continuously falling around the Earth. To avoid falling back into the atmosphere, you have to be moving sideways at an incredible speed, about 8 kilometers per second. That's about 17,500 miles per hour. Think about that for a moment. 8 kilometers per second. That's fast enough to circle the entire world in about 90 minutes. If you fired a rifle bullet from one end of a football field, the International Space Station would cross the entire length of that field before the bullet had traveled even 10 yards. The vast majority of a rocket's energy isn't used to go up, it's used to go sideways, to gain that immense orbital speed. And this is why you can't just slow down when you re-enter the atmosphere. You have to get rid of all that sideways velocity. Doing that with rockets would require carrying an absurd amount of fuel, so much fuel that you would never have been able to get into orbit in the first place. This is the tyranny of the rocket equation. Fuel makes you heavier, and the heavier you are, the more fuel you need to lift yourself. It's an exponential problem. That's why every spacecraft re-entering an atmosphere uses a heat shield. Slamming into the air is the only practical way to bleed off that incredible speed. The fiery re-entry isn't a problem to be avoided, it is the solution. It's the process of converting that mind-boggling kinetic energy into heat, slowing the spacecraft down enough to land safely. It's not about the height, it's all about the speed. Speaking of space, one of the most poignant questions in the book comes from a reader named Brian McCarter, who asked, "What is the farthest one human being has ever been from every other living person? And were they lonely?" The most likely candidates for this title are the 6 command module pilots of the Apollo missions that landed on the Moon. While 2 of their crewmates descended to the lunar surface, 1 astronaut remained alone, orbiting the Moon in the command module. At the highest point in their orbit, when they were on the far side of the Moon, they were about 3,585 kilometers, or nearly 2,200 miles, away from their fellow astronauts on the surface. And because the moon itself was blocking all radio signals, they were also completely isolated from the other 3 billion human beings back on Earth. In those moments, they were the most isolated human beings in all of history. Could anyone else have come close? It's possible. Perhaps a lone Polynesian sailor, blown off course by a storm centuries ago, drifted to a similar distance from any other person. Or perhaps an Antarctic explorer, the last survivor of a doomed expedition, experienced a similar isolation. We'll likely never know for sure. So for now, the title belongs to those 6 Apollo astronauts. Which brings us to the second, more profound part of the question. Were they lonely? After his mission, Apollo 11's command module pilot, Michael Collins, wrote about his experience. He said that, far from feeling lonely or abandoned, he felt very much a part of what was happening. He described a feeling of solitude, yes, but also of connection. He wrote, "I am alone now, truly alone, and absolutely isolated from any known life. I am it." Al Worden, the pilot for Apollo 15, had an even more surprising take. He said, "I was alone, but I was not lonely. I thoroughly enjoyed it. I didn't have to talk to Dave and Jim anymore. On the backside of the moon, I didn't even have to talk to Houston, and that was the best part of the flight." It's a beautiful thought. The loneliest human in history wasn't suffering. He was just a man who was happy to finally have a few moments of peace and quiet. The questions in this book often lead us down these strange, wonderful, and sometimes deeply human paths. They begin with simple curiosity and end with a new perspective on the world. Let's explore one more, a question that seems almost like a riddle, asked by a reader named Vittorio Iacovella. What if a glass of water was, all of a sudden, literally half empty? He doesn't mean half full of air. He means half full of a true, perfect vacuum. What happens next depends entirely on which half is empty. Let's imagine 2 scenarios. In the first, the top half of the glass is a vacuum, with the water sitting peacefully in the bottom. In the second, the bottom half is the vacuum, with the water mysteriously suspended above it. In the first scenario, with the vacuum on top, the result is surprisingly quick and violent, but contained. The surrounding air, at a pressure of 14.7 pounds per square inch, would instantly rush in to fill the void. After a few hundred microseconds, the air would slam into the surface of the water, creating a pressure wave and a loud bang as the shock wave spread out. The glass would shudder, but it would survive. But the second scenario is far more dramatic. If the vacuum is at the bottom, the water is held up only by its own inertia for a split second. The air pressure from above is pushing down on the water, and the air pressure from below is pushing up on the glass. With nothing in between them, the water and the glass begin to accelerate toward each other. In less than 10 milliseconds, they are flying toward each other at several meters per second. Without a cushion of air between them, the water smacks into the bottom of the glass like a liquid hammer. Because water is nearly incompressible, the impact delivers a single, sharp, immense shock. The glass doesn't just crack, it shatters. This phenomenon is known as a water hammer effect, and it's the same principle behind the party trick of smacking the top of a glass bottle to blow out the bottom. The sudden motion creates a tiny vacuum bubble inside, and when that bubble collapses, the shock is enough to break the glass. In our scenario, the bottom of the glass would be obliterated. But the story isn't over. The upward force on the now detached upper portion of the glass would send it flying into the air. It would rise, bang against the ceiling, break into more fragments, and rain back down onto the table. And so we find the final answer to the age-old question. If the optimist says the glass is half full, and the pessimist says the glass is half empty, the physicist ducks. Commentary. As we come to the end of our journey through What If, it's easy to be left with a sense of dizzying, delightful chaos. We've seen planets stop spinning, baseballs trigger nuclear explosions, and the oceans drained away to reveal a new world. But beneath all the humor and the wonderfully absurd scenarios, there's a deeper, more profound message at the heart of Randall Munroe's work. This book is a celebration of curiosity. It's a powerful reminder that the questions we are often taught to dismiss as silly, childish, or impractical are sometimes the most valuable ones we can ask. The world of adults is so often focused on the how and the what is. We learn the rules, the facts, the way things are. But we forget the exhilarating power of asking what if. Munroe shows us that this simple question is the starting point for all true exploration. It's the engine of science, the spark of innovation, and the soul of creativity. When you ask what if a baseball went at 90% the speed of light, you're not just being silly. You're creating a playground for the laws of physics, a space where you can see how relativity, thermodynamics, and nuclear fusion interact in a way that no textbook could ever show you. You learn not by memorizing, but by playing. What's truly remarkable is how Munroe treats every question with respect. No matter how absurd the premise, the science is always real. He pulls from research papers on ICBM nose cones to calculate the cooking of a falling steak, and he uses data on geothermal plant maintenance to estimate the timeline of our world without us. This commitment to seriousness in the face of absurdity is what makes the book so brilliant. It teaches us that any question, no matter how strange, can become a gateway to genuine understanding if we are willing to follow it with rigor and an open mind. So, what can we take away from this? How can we apply the spirit of what if to our own lives? First, I would encourage you to start asking more stupid questions. The next time a strange thought pops into your head, don't dismiss it. Follow it. See where it leads. What if you could jump to the moon? What if trees could walk? What if we lived on a planet with 2 suns? You don't need to be a NASA roboticist to explore these ideas. You just need a little bit of curiosity and a willingness to look up the answers. The journey of finding out is often more rewarding than the answer itself. Second, embrace the power of thinking from first principles. When faced with a complex problem, don't just accept the conventional wisdom. Break it down. Ask the fundamental questions. Munroe doesn't just say it's impossible. He shows why it's impossible by starting with the basic laws of physics and building the scenario from the ground up. This way of thinking is a superpower. It allows you to see the world with fresh eyes and find solutions that others might miss. Ultimately, this book is a love letter to the human imagination and its partnership with logic and reason. It shows that science is not a dry collection of facts, but a thrilling, dynamic, and often hilarious adventure. It's a tool for making sense of the universe, and for dreaming up new ones. That was our exploration of What If? By Randall Munroe. We've touched on some of the most mind-bending ideas today, but I'll be honest with you, a summary can only take you so far. The real magic of this book happens when you read it for yourself. It's in the delightful stick figure illustrations, the witty footnotes, and the sheer joy of discovery on every page. This summary is a map, but the treasure is in the book itself. If anything we've talked about today has sparked your curiosity or made you smile, I urge you to grab a copy. Reading it isn't just learning, it's an experience that can genuinely rekindle your sense of wonder about the world. Also, if you found this journey valuable, please consider liking this video and subscribing to our channel. It helps us continue to explore these incredible books and share their wisdom with the world. Let's keep asking questions, and let's keep growing together.